Today I wanted to talk about hard turning and general machining hardened materials, and the reason for that is because I have to make a bunch of parts that are hardened and relatively precise. So I decided to machine them in a soft state, harden them, and then machine them to final dimension in a hard state. This piece here is 60 Rockwell hard, so it's file destroying hard. If you hit this with a file, it will score the file. I can show you on this part here. That's really hard. Same for these smaller parts back here. I turned them like this out of L2 drill rod, which is 120 to 10 in the ISO world. Held it here, turned it, and pre-drilled it 5 millimeters. Final diameter will be 6 millimeter ID. I'm going to, after hardening now, I'm going to hold it here on this larger diameter, finish turn the whole ID, face it, do this precision chamfer here. There is a relatively precise dimension chamfer on here, and turn the OD. Then I flip it around and just face off the excess. 60 Rockwell is of course not trivial to machine normally, but on the lathe with Cbn tooling it suddenly gets really easy. And I will show you how this works. These here are finished on the OD and ID. I just have to polish up the OD, do the facing, cut precision chamfer on one or two of the parts, and run a lap through the center to clean up the bore. I reamed them slightly undersize, and I'm going to use a reamer and 1 micron diamond lapping compound, clean up the bore and make them a nice fit. Here is the lap, shop-made brass lap for 2 millimeter bore. They're really simple. We'll talk about that later. Over at the lathe, I'm holding the part in a 5C collet, and I have a CCMT turning tool here with a Cbn insert. Usually I buy boxes of Cbn inserts that are used, and then I do a slight regrind or relap on the cutting edge, and for my use then they are pretty good for quite some time. And it's very cheap to do it that way. Normally if you buy a single Cbn insert with one cutting edge, that's about 25 to 30 euros for one insert. Gets very expensive if you buy parting insert or threading inserts with Cbn. I try to do as much on my own with used Cbn. But don't let that stop you from using Cbn tooling. Look on eBay, talk to people who use Cbn on the job and throw them out after when they show signs of wear. Many ways to get going that way. So, doing some facing now. I'm running at about 1200 RPM. When you look hard turning videos on YouTube, most industrial environments run Cbn inserts at crazy speeds and the chip flows off like lava. That works. The Cbn can take that, but I found that if you go a little bit slower, it doesn't hurt. The Cbn cuts just as fine, and you don't have to deal with nearly molten hot chips. And you don't put as much heat into the work, so working to precise dimensions gets easier. You can take very, very shallow passes with a Cbn insert, but also surprisingly heavy cuts. Not with this one, because I reground only a few, maybe 1.5 millimeters of the cutting edge. So let's go. There we go. Now we can take a measurement of the diameter. Should be around 13.28 millimeters. Yeah, that's pretty close. 13.29. Okay. Yeah, we are a few microns oversize. This is the 4mm Cbn boring bar that I made. It has a 4mm carbide shank, which is just a broken shank of an end mill, and I have a small piece of Cbn silver soldered to the end. This tip here is what's doing the cutting action. All the other here is just spare Cbn. And where do I get that Cbn? I'm glad you ask. I got a whole box of these weird Cbn inserts. These go in a face mill for hard facing. I think that's made by Lach Diamant. That's a German company. They make Cbn and diamond tooling, and it has a convenient large piece of Cbn, silver soldered or brazed in there. And if you heat this up with a small torch, you can take this piece of Cbn and just pull it off with a pair of tweezers. And it has already silver solder on the back side because it was silver soldered in there. And then you can take your carbide blank, you flux it up, you put a little bit of silver solder on it and let it flow. Apply more flux, drop on your piece of Cbn, hold it in place, heat it up with the torch, let the solder flow, and then you have a Cbn boring bar, which normally would cost you an arm and a leg. Then I ground it to shape. You can grind Cbn on a normal diamond wheel, on a resin-bound diamond wheel. Takes relatively long to grind it compared to carbide. The cutting edge needs preferably to be lapped. Robin Renzetti talked about lapping Cbn tooling on Instagram quite a lot, and that's definitely the right way to do it. I usually use a D40 diamond wheel, which is very fine to finish grind my Cbn, and it seems to work okay-ish, but I'm looking to get a diamond lap, a ceramic lap with diamond on it. You cannot not really use a cast iron or aluminum or copper lap for lapping tools like this, because when you present it to the lapping disc, which is relatively soft material if it's not ceramic, the cutting edge will dig into the lapping disc and create havoc. So that's the reason why a ceramic lap is a good idea. Cbn usually gets ground. Cbn in general is neutral and has a tiny negative rake edge break. I think it's called a K-land. If you grind it positive or even neutral, it usually doesn't stand very well. So that's the magic behind Cbn. You can see the reflection of this edge chamfer here, and that's the negative raked chamfer on the cutting edges that I talked about. Of course, in front here, in cutting direction, we have that too. A little bit hard to show. Here you can see the reflection of the negative rake. I should have bored the bushing in a soft state a little bit larger. Hard turning from 5 up to 6 millimeters is a bit annoying, because to get a boring bar in a 5mm bore, it has to be quite skinny. This one doesn't even fit, so I have to take a fairly beefy cut on the first pass to get the boring bar even in the hole. And it's a fair bit over center, which is also not ideal. So this is going to be a little bit squeaky. Oh, by the way, the chips created by hard turning, especially the very fine dust that we get now from the ID boring, this is really deadly for your slide ways on a machine. There is a good reason why this machine has all its ways covered. Okay, took me a few passes to sneak up on the final dimension, but I hit it pretty darn good. A tiny amount, about 3 to 4 microns oversize to 6 millimeters. I don't have a 6 millimeter gauge pin here, but I have a 6 millimeter carbide shank, which is 5.99, so 10 microns undersize. That's a nice sliding fit. So now we need to cut a relatively precise chamfer. Now we have to cut a relatively precise chamfer at 8.5 degrees, 0.15 millimeters wide. So I could grind a custom tool for this, but with CBN that's not really economical, because even a used CBN insert costs quite a bit of money. We're not going to do that. I prepared this earlier. I saw Robin Red said he'd do this. He just takes a regular CBN insert and he clamps it at an angle in a tool holder like this to do certain chamfers. And I tried it, and it works. It really works well. This one here is set up to do the 8.5 degree chamfer, and this one is set up to do an 18 degree chamfer. And the way you set this angle is relatively simple. You do your math and you calculate your triangular relationships. I did the math for 2 millimeters of travel in diameter. That results in a C travel of 0.29 millimeters. And to do this, we get an indicator in here, and we drop it here against the cutting edge. Move it to a convenient dimension, like 0. Then we move our DRO, or x-axis, according to the DRO 2 millimeters in. And we look at our dial test indicator, and when we get our 0.29 millimeters, the angle of our cutting edge is correct. And if not, we loosen the screw very carefully, and we take a small copper drift and we move the insert around until we get the correct angle. Okay, here's a better view. I'm running the tip of the indicator along the cutting edge of this insert. And I moved exactly 2 millimeters, and I got 0.29 millimeters of travel here. So that's correct. Okay, how to figure the angle dimension relationship out? You need to know the angle you want to go. In this case, 8.5 degree. Then you draw yourself the triangle. This is just for helping. This angle is 8.5 degree. Then you take an arbitrary number, like 2 millimeters. That's the length you're going to sweep over the cutting edge of the insert. And this down here is x. This is how much the indicator has to read. So if you look our trig functions up, this is tangents of the angle, 8.5 degree, equals dimension x divided by 2. We pull over 2 by multiplying. Tan 8.5 degree multiplied by 2 equals x. X is equals, you hit this in your calculator of course, tangents 8.5 multiplied by 2.2 multiplied by 2 gives us 0.298. 0.298. So yeah, that's the way to do the math on how to set your cutting tool at a precise angle. And why do you not just put the compound on and cut it with the compound? Because that's annoying. If you do that, you lose all your offsets of your tooling in the DRO. And if you have to do multiple parts, it's even worse, because then you're just swinging around the compound like crazy all the time. So I prefer to put the tools on an angle. I plan to design a lathe chamfering tool that can be set, that has a small dial that can be set for angles. Very much like the adjustable angle chamfer mills. Okay, this is easy now. We're just touching off on the corner. I'm going to glue it up, and then I'm feeding in 0.5 millimeter in C direction. Okay, part finished. You saw me facing off the other side and turning it to final dimension. Should be relatively close to 16.3. And the ID gauges very nicely with a carbide shank. That's usually 10 microns undersize. When I push the pin, I use this like a gauge pin, through, there is a little bit of a resistance in one spot. It's not very bad, but I might run a lap through it to get it nice and straight. Let's see, this is a dowel pin. A dowel pin is usually a smidge oversize. This one is, yeah, it's about 5 micron oversize. So let's see if this goes in. This should be, yeah, it goes in, but on the weird spot that I felt with the other one, it doesn't go through. Yeah, the bore is a little bit bell-mouthed on both ends, as far as I can tell with the pins. Gauge pins, or pins in general that you use on a bore, can tell you a lot. Gauge pins are usually one of the nicest way to check bores in my mind. You get a feel for the diameter, you get a feel for the shape of the bore, you can check the ID, the position, and a lot more just with gauge pins or with known good other pins. This is 5.99, this is 6005. So I know the bell mouth in here is roughly 6.00 millimeters in diameter. Just with 2 very inexpensive pieces of stuff to check it. So next we'll have to polish up the OD of these parts and face them to length. Not much work on these, one gets chamfer again. I'm using a jeweler saw to slit this piece of 6mm round brass to create an expanding lap, to lap the idea of those two bushings to final dimension. Next I will drill and tap the end for a screw, and when I jam the end of the screw into the lead out of the thread, it will expand the lap. Okay, I have the brass lap. I drilled and tapped the end for an M4 set screw. The set screw runs in the end of the thread and expands the arbor. Just holding it in a drill chuck, running it at 500 RPM. I have some 1 micron diamond compound here, lapping compound, and some WD-40 for lubrication. So we apply a little bit of the diamond. Take our first bushing, slip it over, add a little bit of lubrication. We need a little bit more drag right away. Yeah, that was a little bit too much. I'm adjusting the set screw and I move the part up and down to feel the drag of it, and this seems good now. So now we just let the machine run and do our lapping, which is an endless up and down. This black smudge you can see here, this is the abraded tool steel. I switched to 3.5 micron diamond paste because the 1 micron went about as slow as continental drift. So applying a little bit more, I'm almost there. I cleaned the bushing with isopropyl alcohol, blow it out with compressed air, and rinsed it again with isopropyl alcohol. I checked the dowel pin if it's straight, otherwise you get very weird results. I just spun it in a V-block and put a dial test indicator on top. And when we check the bushing now, that's exactly the fit I was after. A very nice sliding fit on a 6005 millimeter pin. Okay, I'm trying to show you difference in finish here. The left bushing is only hard bored with the Cbn tool, this one, and the right one is lapped with 3.5 micron diamond. As you can see, the right one has a really shiny finish, and due to the macro lens it's really tough to get it in focus. So you see that the tooling marks are pretty much gone, and I have this shiny surface. Not a really gauge quality, but for the purpose of this bushing, way good enough. And this one is just hard bored. So you see some tooling marks in there and some dirt. This angle you can see the tooling marks very much. So that's the reason why I'm lapping these. and also the bores have some shape to them. Okay, I lapped all the IDs for these 6mm parts, and I got them to a very nice fit. Very nice sliding fit, but it doesn't fall out. So we're very close to an interference fit, which is perfect. These parts, in operation, these parts need to be sliding because they will be spring-loaded with some heavy bell wheel washers and perform the metal forming this tool is going to do. Here is the lower body. This is three-part. This is the lower body, it's this disc, and this bushing. This all goes together. And I lapped the bore in the body and in this disc. So this is also a nice sliding fit, because this bushing will be spring-loaded from down here with bell wheel washers too. Next step will be to lap the 2mm ID holes in these bushings. So this 2mm pin that I'm going to use as a guide fits through all the way. These are reamed, but reaming and then hardening usually leads to a smaller bore, because most steels grow a tiny amount when hardened. And the lap for the 2mm holes is just the same as the 6mm one. Piece of brass. I slid it with a tiny abrasive cutoff wheel with die grinder, and there is no room for a central expander screw, so I'm just using a small screwdriver in the slot, and by twisting the screwdriver I flex and expand the arbor, the lap, by bending it a little bit. These are available commercially. Tom Lipton showed these once. There is something called like ear hole lap or needle hole lap or something like that, and I cannot get them here. I can get very high-end laps from a Swiss company for small diameter bores, but those are ridiculously expensive, so I make these myself. That's what we're going to use to clean out these bores in these small bushings. Back at the milling machine, that's the small arbor and small lap. I'm applying some 3.5 micron diamond paste. This one does not have grooves for the diamond compound, because I figured that the large expander slot that I put in is enough for this purpose. So then we try to get this on here. Add a little bit of WD-40 and go for it. 1000 RPM. And the 3.5 micron really cuts fast. A few seconds and we have a very nice fit here. They are drilled for clearance from the back about 2/3 up. So it's easy to put them on the lap that way. Okay, there we go. Second one. Nice sliding fit. And you might have noticed that I didn't have to expand the lap as so far. I expanded it once a little bit over 2 millimeters. And this design allows for some spring back. So if you push it over a bore, it almost works like a flex hone that you use for engine refurb, hydraulic refurb, stuff like that. This kind of follows the shape of the bore a little bit, but when you have when you pay attention on how the part drags on the lap, you can very precisely and very accurately control the shape of the bore. This design also has the drawback that you can create a bore that's not straight. If you hold the part very much at an angle, it will create a weird shaped hole. I just love this. It's a little bit tight on the end. I will deal with that, but it's really close. But always keep in mind, these are all hardened components we're working on. Okay, this is good. And those few seconds of lapping you just saw, that changed the shape of the hole enough so this pin now goes in with a constant force over the whole length, measured with my calibrated right finger. Yeah, very constant. Showing you how to remove the CBN from one of those inserts. Works the same for any other standard CBN insert with a carbide or steel body. Using oxy fuel torch, I think you can get it off with something like a map torch too, but with the oxygen added, the flame is much more intense and you have a better chance of getting the CBN off before you die of old age. Setting for a nice flame. That's a nice flame. I'm using a tungsten TIG electrode as a poker. Heating it up. This insert just sits in the slot of this aluminum fixture, and this aluminum fixture obviously is way colder than the environment because I get a lot of condensation on it, but that's not an issue. There we go. There is the CBN. There is the steel body. This goes in scrap. And here is the piece of CBN. It has already a ground cutting edge here and here. The radius here on the back, that's just a radius. And now you can take this. The back side already has silver solder or copper braze on it. So I didn't show you how I did the brazing or silver soldering on the carbide boring bar that I used, or CBN boring bar. But let's have some fun with this CBN that I just unsoldered from the milling insert. Let's make a DCMT CBN insert. I took an old DCMT carbide insert and I ground a large step here, just holding the insert with the vice grip up to a diamond wheel of the D-bit grinder. And the CBN, the chunk of CBN that I have, fits in here right in place, like it belongs there. So let's do this, and then we'll do a grind on it. Oh, that's very elegant. So flux it. Because somebody will ask, this is Fontargain F300H Ultra NT. Ugh. Add a small dab of it. We don't need a ton of it. Especially not where we do not want solder. Now we're going to put some silver solder on there. I have some Jet A 30% 1mm silver solder here that I'm going to use. And again, my small micro torch. So we're going to heat this, then we add some silver solder. Okay, there we go. Now we take our CBN, place it here, and hopefully it doesn't fly off when we start to heat it. Let's try it with a little bit more of a gentle flame. Last flame was a little bit aggressive. There we go. This won't win a prize. But all my CBN tooling is butt ugly and it works. Looks like we have a half decent joint. Looks really butt ugly with the large chunk of CBN on top there. And now we'll just shape it on the diamond wheel in the rough shape of the DCMT insert so we can put it in an indexable lathe tool and go from there. As with all materials that we're grinding with a diamond wheel, CBN will probably kill you, so I'm using dust extraction. Okay, there we go. We got our beautiful CBN insert almost to shape. Of course, this is thicker than a regular DCMT insert, but you just have to adjust your height on the tool to get it working. Now we change to a finer wheel, a D40. If you wanted to do a very good job, you could make an holder for the insert and do a machine grind on it. But I find that most of the time offhand grinding is good enough. So we start by grinding the top, cleaning it up. Then we're going to grind the sides, always with the grinding wheel cutting into the cutting edge. Always the wheel spins like this, and we're always grinding into the cutting edge. That's also the reason why for the second side you will see me going over to this side and holding it very awkwardly from behind. Okay, now as we have ground our beautiful, ugly insert, we will have to put a tiny edge break on the cutting edges. 5 degree negative, 10 degree negative, something like that. So roughly like this and like this. First side like this, so we're again grinding into the cutting wheel, and for the second side I'm switching over to the back side of the grinder and try to get it. Yeah, that works. Okay. Okay, try to get a close-up. It looks really not very good. Grinding this insert with the hands around the camera is not the easiest thing. But you can see this is the edge brake that I put on with about 15 degree. Same on this side here. You can also see that on the insert I scavenged the CBN from, it's already a sandwich construction. You have the CBN and it's bonded somehow in, I don't know how, to a piece of steel. You can also, if you have a regular CBN turning insert like this trigon shape here, instead of removing the CBN and just putting the CBN back on another carrier, you can take the whole insert and silver solder that onto a body. That works especially if you're making a larger turning tool, boring bar, threading tool, whatever. And as you can see, when you buy a CBN insert, they give you usually one cutting edge. That's one. So yeah, they are expensive. Surface finish on the grind on my insert is okay-ish. It could be better. Robin uses a diamond, a ceramic lab with 1 micron diamond. But this will have to do for now. Let's go to the lathe and give it a shot. Okay, got a nice high quality, very dull Fraser high-speed steel end mill here with a rock hard shank. We even have an interrupted cut, so we'll see what happens. Okay, I was running 1mm depth of cut on the second cut, and the CBN could not stand the interrupted cut of cutting through the weldon flat here. But until it got there, it cut a beautiful chip. You have to admit that. It really cut very nice. It's high-speed steel. It's 60-something Rockwell hard, so that's not a big deal because we can just touch up this front edge and go on. So I think that goes to show that you can regrind Cbn tooling, repurpose Cbn tooling on a very with relatively low amount of tooling. You need something to silver solder, map torch, or even better, oxy-fuel, and you need a diamond wheel that's reasonably fine, preferably a diamond lap if you have one. But even with a D40 diamond wheel, you get really far. Okay, here are the parts that we just made or finished. Main thing I wanted to show is the hard turning with the Cbn tooling, and also the very simple tools that you can use to work on very hard materials, to finish size a bore, and yeah, just do some machining on those. The larger parts of this forming tool, forming die set, these are 12311 tool steel, which is something like H13, I think, and these will be plasma nitrided. I didn't want to go through the trouble of hardening these and hard turning these, because they do not need to be as hard as the internals here. They just need to be hard, and some of the surfaces like this one here needs to be polished after hardening or plasma nitriding. Plasma nitriding is a process that gives almost like a case hardening with relatively large depth and doesn't change dimensions at all. An IT7 class tolerance field will not change during plasma nitriding. At least that's what the guy from the nitriding place told me. We will see when these parts come back. I got the permission to show this tool, but absolutely not the parts that are going to be made with this. I can show something with a dummy part, so once I get the parts back from plasma nitriding and I made all the accessory parts, and I put in the bell wheel washers, the disc springs. These are some serious disc springs. There's some force involved. Then I will put it all together and show you how this works. It's quite ingenious. I didn't design this, of course. So yeah, but I wanted just to show you the basic principles with a simple lap like this, the hard turning and stuff like that. Hope you enjoyed. Thank you all for watching, and see you next time.